G'day! Now it's time to keep going with this fabulous story of trigonometry because there's so much stuff jam-packed in that wonderful curriculum. It's probably a bit too much to process, too much to take in, but there it is, and I need to attend to it now. It's the topic of trig identities. Now, I've been playing with them a little bit in earlier videos and the last video, but now it's time for me to attend to them properly. In fact, there's a particular set of trig identities I need to talk about, the sum and difference formulas they're called. But to get our brains going, let's just get our minds back to circumlometry, because circumlometry is the true story here. And we were seeing trig identities back then. For example, here's the sun moving a circular path, radius 1 great big astronomical unit, at some angular elevation x. If I say, okay, well, what's the sine, the height, and the overness if I add an extra 360 degrees to that angle? We say, well, that's not much, because if I add an extra 360, it just goes around some more, and I'm back to the same place I was before. So a trig identity would be a sine of x plus 360 is just sine of x, same height. Cosine of x plus 360 is just cosine of x, same overness. Adding 360 degrees doesn't matter. Grand. We also saw things like this. So we're doing a positive angle x, while we do a negative angle of elevation. Well, then you realize, oh, so you're going up a height of sine of x, you'll be going down that same height. In fact, it'll be the opposite direction. Sine of negative x will be the opposite of sine of x. Overness won't change. Same overness of positive angles or negative angles. Cosine doesn't change for negative angles. And also, of course, we've got the very famous identity, the Pythagorean identity. Pythagoras' theorem says that this side squared, sine squared, plus this side squared, cosine squared, equals this side squared, 1 squared. Sine squared plus cos squared equals 1. And in video 8, we actually saw more. We started flirting with some good ideas. For example, back there we said, look at the cosine graph and now make the number 90 behave like 0 in that graph. You say, okay, so if you think of the cosine graph, it does this, like that. You say, okay, now make x equals 90 behave like 0. So we're starting at 0 now, make that all starting at 90, and you see you get a graph that looks like that, and we saw that's exactly the sine graph. And we also did the same thing with sine. This time make x equals negative 90 behave like 0. So here's the sine graph, and we made negative 90 behave like 0. So we'll take the sine graph and make negative 90 behave like 0, and it now looks exactly like the cosine graph. So there's some more trig identities. In fact, let me put them up the list here because I am going to use them because they are actually kind of lovely. It says I can convert sine into cosine or cosine into sine by adding or subtracting a 90 degrees in one of the inputs. Great. So actually, this shows sine and cosine are very intimately related. So once I've already got information about the cosine, I've already got information about the other. Great. But look at this. What I've got here is a formula for cosine of the difference of two angles, an angle x and an angle 90 degrees. It turned out to be a very simple formula. And here I've got a formula for sine of the sum of two angles, an angle x and an angle 90. It turns out to be a very simple formula. So it's very natural then to ask, well, about the topic of this lecture, this video. What if I did the sum and differences of not just x and 90 degrees every time, but x and any other angle y? Sum and difference of two general angles x and y. And I guess the formula is probably more complicated, so who knows what they are? That's what we need to find out. Can we work out the sum and difference of cosine and sine? Can we work out the sine and cosine, the sum and difference of different angles? So I guess technically there's going to be 4 formulas we want. Cosine of a difference, cosine of a sum, sine of a sum, and also sine of a difference. But as I said, I have a feeling once we've got the sines, once we've got cosines figured out, we can do this sort of thing. Once I know about cosines, I get sines from cosines by putting in 90 degrees. I'll do that. So I'm not going to worry about sines. Also, I have a feeling I don't need to worry about sums and differences. I can think of a sum as really a difference formula. It's cosine of x minus y. So if I know a formula for a difference, then I really have a formula for the sum. I could use x and negative y. And once I've got negative y's floating around, it's okay, I know what to do with negative inputs. For sine, it'll just change the sign of the sine, and for cosine, it won't do any effect. So I have a feeling, actually, everything will boil down to getting one formula. Once I've got one formula, all 4 will follow. Now I'll do that, because that was too fast. There's a lot to take in. It was very abstract. So I'll actually do what I just said. But my first task is get a formula. So I'm going to go for the one that I've just put in a box. I want a formula for the cosine of the difference of two angles. Now, there are many proofs out there. I'm sure you have textbooks with proofs in it. And a lot of the proofs assume we're still in the story of trigonometry. So they'll draw lots of triangles, which is great, perfect. But that's assuming x and y are angles that are relevant for triangles, always between 0 and 90 degrees. But actually, we want an identity that's true for all angles, for the true circumlometry story. X can be any angle you like. So I'm going to do a proof of this, a derivation of a formula for the cosine of the difference of two angles in the circumlometry story that will work for all angles, no matter how big or small they are. Great. So to do that, I'm going to go for this one. So I want a formula for the cosine of x minus y in terms of cosine of x, cosine of y, sine of x, and sine of y. So, did I say it the right way? Well, all four things. So it means I want to play with an angle of elevation x, an angle of elevation y, and look at the difference of those two angles of elevation. So I'm going to draw a circumferential picture with all those angles in it. So I want a bit more space. So let me just do this. Maybe I'll redraw this one. I have a feeling I'm going to use all that basic information there. Let me just draw maybe just the top half of the picture. So here's a circle that goes all the way around, but the rest is going off the screen. I want a point with an angle of elevation x, all right? X is from the eastern horizon up that way. Great. Now, let me not draw the overness and the height because this picture's about to get very complicated, okay? So, but I will record it this way because actually we do know the coordinates of that point. This overness is normally called the x-coordinate and this height is normally called the y-coordinate. Well, the overness, the x-coordinate, is actually cosine of x. The height is actually the y-coordinate, is sine of x. So this point actually has coordinates cosine of x, sine of x. Now let me get an angle y in. Okay, I'll do a big one, an angle y, something like this over to here. Angle y. And again, I actually know its coordinates. Let me not draw the lines in, but I know its x-coordinate is cosine of y, and its height, y-coordinate, is sine of y. So this is actually the point cosine of y, comma, sine of y. All right, my handwriting and my drawing is atrocious, so hopefully you're following in principle. Maybe redraw these things as you go along, or take this slowly if you need to take it in. But that's it. There's a point angle of elevation x, angle of elevation y, and I've actually got the difference because here is the difference of those two angles. It'll be the whole angle y minus the angle x. It's actually y minus x. Oh, interesting, because I think I want a cosine of x minus y, but it looks like I've got y minus x instead. I wonder if that's going to throw me. Oh, no, let's keep going. Let's keep going. Now here's something really clever. So I didn't think of this, but someone said, you know what, do this. It's going to be magical. I promise you. They said, try to work out the distance between those 2 points you've got. And you say, okay, I guess I can because this is just like geometry now, coordinate geometry. I know the distance formula. The distance formula says the distance between 2 points is the square root of the sum of the difference of the x value squared and the sum of the difference of the y value squared. So you do the difference of the x value, square it, difference of the y value, square them, take their sum, square root of all that. Yeah? Great, so I could do that. But you look at these coordinates, they're horrible. They're going to be hard to write down. It's going to be very messy. So then do this. Say to yourself, okay. That picture is going to be complicated. Could I make some of these points easier? And one thing you say is, well, yes, I guess you get the same distance. I just took this whole picture and rotated it. So actually, one of the points ends up landing down here. I'll bring this point down here, bring this point over here accordingly, bring the purple line over this way accordingly. In fact, I'll do that. Bring this down at an angle x, gets me right there. Bring this over an angle x, gets me right there, say. And then this pink purple line will be moved over this way here. And since nothing's changed, it's just a rotation, it's the same distance d. Whoa! So I've just actually rotated everything x this way, which means, oh, angle hasn't changed. Messy, messy, messy. But that angle there for that blue chord is still y minus x. All right. Oh, but then think about this. These points are easy. This is the point right on the x-axis on that circle. It has x value 1, y value 0. And this point is actually the angle of elevation of my sun at angle y minus x. Its x-coordinates is overness, its y-coordinates is height. It has coordinates cosine of y minus x, sine of y minus x. All right, probably hard to read. But there I have it now. Oh, I don't know if it's helpful though. But I've got the distance as the difference between those 2 points. And I've also got the distance as the difference between those 2 points. Well, let's work out the distance both ways and see something magical happen. Here goes. Distance is the square root of the difference of the x value squared plus the difference of the y value squared. I don't want to work with square roots, so I'm going to do this. I'm going to work out the distance squared instead. Let me do the pink one first. I don't know why. The distance squared will be the difference of the x values squared. The x values are cosine of y, difference cosine of x squared, plus the difference of the y value squared, sine of y, minus sine of x squared. All right, I'm going to do it. I'll get that thing squared, and cross terms. That thing squared, and that thing squared, and cross terms. Let me do all the squared part first. I'll get cos squared of y plus cos squared of x plus sine squared of y plus sine squared of x plus the cross terms, minus 2 cos y cos x and minus 2 sine y sine of x. Okay, I'm not really having fun. Oh, but sine squared x, cos squared x. Sine squared plus cos squared is 1. Sine squared y, cos squared y. Sine squared plus cos squared is 1. So I've got 1 and that stuff. I've got the number 2 minus 2 times the cosine of y, cosine of x, minus 2 times the sine of y, sine of x, and that's the distance squared. All right. Using the purple line, that distance squared is that icky formula. Ugh. All right. Let's keep going. Let's work out that same distance squared now using the blue formula, and let's hope it's less icky. All right, let's try it out. Bad handwriting, good luck reading this, but here goes. It's the same principle. The difference squared is difference of the x values squared, cosine of y minus x and 1. Cosine of y minus x with the difference of 1, all squared, plus sine of y minus x and 0. Sine of y minus x minus nothing, all squared. All right, now I'm going to be a little bit fast this time because I see when I expand this, I'll get this squared plus this squared in cross terms and just that squared. But look at this, I'll get cos squared and sine squared. Cos squared and sine squared together make 1. Icky angle, but cos squared plus sine squared gives me 1. So I get 1 plus negative 1 squared plus another 1. And the cross terms, minus 2 times 1 times cosine. 2 times cosine y minus x. Oh, that's much friendlier. So d squared is 2 minus 2 times the cosine of y minus x. So there's a second formula for the same distance squared. And since it's the same distance squared, these formulas must be identical. 2 matches, yes, minus 2 times stuff. Well, here I get cosine of y minus x for my stuff, and here I get cosine of y cosine of x plus sine of y sine of x for my stuff. So I've now gotten, where am I going to put it? Where am I going to put this? This is it, this is the formula. Ghastly, but it's what it is. I see that this cosine of y minus x, that part of the formula, y minus x, must match this part of the formula, which is cosine of x, cosine of y, plus sine of x, sine of y. Whoa, whoa. And let me get rid of all this now, because I've got it, and grand. Now, fix this up to what I want to do to get all 4 formulas. For starters, I really wanted cosine of x minus y, if you remember. Well, let's get a brighter marker, but that's bright enough. Well, that's not too bad, because I can think of cosine of x minus y as cosine of the opposite of x minus y, which is cosine of y minus x, which is that formula. So actually, it is this formula. Cosine of x minus y is that. Beautiful. Beautiful. Okay, you know what? Trigonometry just ain't nice. That is a horrible formula. Who would guess that? Well, we could check ourselves. For example, we should be able to get back to that formula from it. For example, if I did do cosine of x minus 90, I would get cosine of x, cosine of 90, which is 0, plus sine of x, and sine of 90, which is 1, and something times 0 plus 1 times sine of x is sine of x. Beautiful. Looking good. All right. Now, getting other formulas from that. Cosine of x plus y. Well, the key there is to think of that as cosine of x minus y. It's the same thing. In which case, now it's the difference of 2 angles. Just copy that formula. That'll be the cosine of the first angle. Yep. Cosine of the second angle, negative y. Plus sine of the first angle. Yep. And sine of the second angle, negative y. And I know what cosine of negative y is. Cosine of negative something just doesn't matter. And sine of negative y is the opposite. So this is actually cosine of x, cosine of y, because that doesn't matter, but it does matter here. So I get a sine come out, sine for the sines comes out, sine of y. Cosine of x plus y is cos x cos y minus sine x sine y. Okay, great. Let me keep going. Let me write that on the board to get more space, because this is just ghastly. I hope you don't have to memorize these things. And if you do, I will say, let calculus save the day. I'll show you what I mean by that later on. Sine of y. Okay. All right, keep going. Suppose I wanted now sine of x plus y. Okay. We've got it, we've got it. I'm going to use this. Sine of something is just cosine adjusted by 90 degrees. So this is really cosine of x plus y minus 90. Once I've got that, because I can think of that as cosine of x plus y minus 90, the summation formula. In which case, this is cosine of the first angle, cosine of y minus 90, cosine of y minus 90, minus sine of the first angle, sine of y minus 90. Now to think of these things, okay, so what is this going to be? Cosine of x is fine, cosine of y minus 90. Do you have it on the board? Oh, cosine of y minus 90 is just sine of y. This is cosine of x, cosine of y, sine of y. Minus sine of x and sine of y minus 90. Oh goodness, okay, so I want the sine curve, but now with 90 behaving like 0. And I can see, oh, it's going to look like this. It looks like the upside down version of cosine. It's actually negative cosine. This is actually negative cosine of y. Negative makes that a positive. Whoa. So there is a formula for the sine of the sum of two angles. And then I can get the sine of the difference of two angles by using negative y in there and working out how it adjusts. Crazy. All right, so there are the formulas for the sum and differences of sines and cosines of two angles. Some people say, please, we might want to do the double angle formulas. For example, I desperately need to know a formula for sine of 2x. Oh, which is sine of 2x, think of it as sine of x plus x. So it'd be cos x sine x plus sine x cos x. Oh, 2 sine x cos x. Bingo! Or if I want the cosine of 2x, I guess I'm going to go with this one. Think of it as cosine of x plus x would be cos x, cosine of x minus sine x sine x. Cos squared x minus sine squared x. Which is not quite Pythagorean because I've got a minus sign there instead of plus sign now. Which makes sense because cosine of 2x would be all sorts of numbers. Great! Everything follows through. You could work out your triple angle formulas. What's sine of 3x? I'll probably think of it as sine of 2x plus x. Great. Great, great, great. So there we have it. That is quite the enterprise here. And this is just hard. I admit, these formulas are not natural. You would not think to guess these formulas necessarily, unless you're a much more cleverer person than I am. I wouldn't guess these formulas. Except, okay, I'm going to stop there, but it's going to have a little bonus moment, because if you know some calculus, there's a lovely thing that makes all these things just stick in your head. In fact, there's a wonderful discovery by Leonard Euler and others in the middle of the 1700s said, do you know what? Complex numbers are key because they make trigonometry ridiculously easy. It makes these formulas suddenly very natural that you can actually get them in your head without even doing any work. They'll just work them out in your head. I'm going to have a pause. This is beyond the standard curriculum, so we'll stop here and we'll stop there. Or if you want to see a little bit of calculus, I'll show you a way to get to it from calculus. Get to these formulas with absolute ease. That actually I do have these formulas in my head only because I quickly do a quick calculation that makes it easy. All right, on that strange, mysterious note, I'll see you in a moment if you want. So a lot of people often ask me, why do we need to know complex numbers? They often introduce early in the curriculum when you're solving quadratic equations, please write your answers in terms of 3 plus or minus I all over 2. Why? What does it do for you? As far as I can tell, really actually kind of nothing, really, actually at that level of thinking. But here's the thing, complex numbers are fabulous because they actually unite so much mathematics in ways that are astounding. In fact, one of the greatest surprises of history of mathematics was the discovery that complex numbers actually make trigonometry ridiculously easy. It happened in the middle of the 1700s. Many people wrote about this, or it certainly has his name attached to it as well, but other people are aware of it as well. It's this phenomenon, but I need to know some calculus to explain it properly. So hopefully you have seen a little bit of calculus. One thing you learn in a calculus class, there's one particular function that's particularly nice. It has the easiest derivative beyond being trivial. The derivative of the function e to the x, amazingly, is just itself. Phenomenal. It's phenomenal. It's actually beautiful. So there's a very natural function in calculus. The derivative of e to the x is actually itself. Makes life so much easier. In fact, it's really easy to say, if I've got a differential equation, I'll think of a function as derivative as itself, and say starts out at the value 1 at x equals 0, then you say, oh, it must be just e to the x, because there it is. Voila. But actually you go a little bit further. If I want a function whose derivative is twice itself, you can say, oh, it must be something close to this, and you realize, oh, y equals e to the 2x works. The derivative of e to the 2x will be derivative of e to the 2x is e to the 2x times the derivative of what's inside, 2. Little chain rule. In general, for any value k, the function whose derivative is itself, starting at the value 1, has the answer y equals e to the kx. Great. Now, let's get quirky. Let's get quirky. I kind of assumed there that k was a nice real number. Well, if I did e to the ix, e to the ix, that's what I have to be. Be a little bit weird. So, oh, if I've got a function whose derivative is I times itself, it must be e to the ix. But then look at this. Look at this function. Y equals cos x plus I sine of x. Let's take its derivative. The derivative of this thing is the derivative of cosine is negative sine of x plus I times the derivative of sine is cosine. Let me pull out a factor of I, because I could think of this negative 1 as I squared sine of x plus I cosine of x. So this is really I times I sine of x plus cosine of x, which is what I started with. So actually, this formula also fits this differential equation. And also put in x equals 0, I get cosine of 0, which is 1, plus I times sine of 0, 0 is 1. It fits. So if you believe that this mathematics extends to complex numbers and these have unique solutions, then I say, oh my goodness, this solution and this solution must be the same thing. It must be the case that e to the ix is cos x plus I sine of x. Whoa, whoa. In which case, trigonometry is really just exponents in disguise. And all those sum and difference formulas are actually just exponent rules in disguise. Let me show you. Let me show you. For example, I'll do the first one. We worked out sine of 2x and cosine of 2x at the end of the last video. Okay, so let's do it here. But here's how I'm going to do it. I'm going to think of e to the ix squared, which is really e to the I 2x by the standard exponent rules. This is really, for what I just learned, cosine of 2x plus I sine of 2x. And this one here is, e to the ix, cos x plus I sine of x squared. By the way, I'm being a bit of a mathematician now. I've dropped writing parentheses because they get clunky after a while. Mathematicians get a little bit lazy, stop writing parentheses here. They should write parentheses, but it's kind of understood. I don't need parentheses there. Look, I use them there though because they're kind of needed. So I oscillate between using parentheses and not. In high school, well, it's bad of me not to be consistent, but I'm being a mathematician now was, okay, we all know. Anyhow, e to the ix, cos x plus I sine x squared, cos squared x. Plus I sine of x squared, I squared sine squared, negative sine squared x, and the cross terms plus 2I sine x cos x. And I see I've got this answer, and I've got this answer, and I can say, cosine of 2x has no I stuff attached to it, so it must be that part and that part. Cos of 2x must be cos squared x minus sine squared of x, which is what we got last time. And the I part is sine of 2x here, and the I part here is 2 sine x cos x. That's what we had. Sine of 2x was 2 sine x cos x last time. Whoa. To get our addition formulas. Suppose I want to play with sine and cosine of x plus y. So just think of, sine and cosine of x plus y. Well, what do the exponent rules tell me about that? That tells me, that's just e to the ix times e to the iy. That's it. That's the exponent rules. Okay, so let's unravel what that means in terms of back to trigonometry. Well, this one on the left is cosine of x plus y plus I sine of x plus y. And the stuff on the right is cosine of x plus I sine of x times cosine of y plus I sine of y. Yeah, I'm really oscillating between parentheses and not. My marker's running out. Okay, let's try this one. All right, this equals this equals this equals this. Let's expand this out. This equals, let's do the real part. So this is the real part, stuff without i's. So it will be a cos x cos y, cos x cos y. I'll get i's there, I'll get i's there, but I will get no i's here. I times sine x times I times sine y is I squared minus sine x sine y. Cos of x plus y is cos x cos y minus sine x sine y. And actually, I do that in my head. I do that in my head. If you ask me to memorize those formulas, well, I don't memorize them. If you ask me to recite those formulas on the go, I quickly do that in my head. And the I part plus I times, that'll give me the sine of x plus y, will be the I part here. I get this from sine x and a cos y. And another I part will come from a sine y and a cos x. Messy, 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 but there it is. They are the trig identity formulas we had moments ago. Brilliant. So I bet you could play with e to the I 3x. Think of that as e to the I x cubed, and you'll have the triple identity formulas for trigonometry if you want. I bet you could do the difference formulas. Play with e to the I x minus y, what the exponent rules say about that, and then what does it translate to when it comes to trigonometry. You'll have all the difference formulas. They're all there. This is a stunning shocker, absolute shocker in the history of mathematics, and it's why complex numbers are actually so valuable. Those trig formulas are miserable. They are miserable. Suddenly, when you see they're just really exponent rules in disguise, life is so much easier and beautiful. Thank you, complex numbers. I don't know what you are, you're imaginary, you're complex, you're strange, but you make the math unified and beautiful and bring it all together. Absolute joy in mathematics, absolute surprise in trigonometry. You've just got to be just compelled and in awe of this sort of thing. Love it.